Hello everyone, this is Lecture 3 of ComSci 174, Image Processing. In today's video, we will discuss image processing and look at techniques like histogram equalization, thresholding, morphological transformations, and filtering. Okay, so let's start. So in image processing, of course, we are processing an image. So let's remember that an image is basically just a grid or matrix of intensity values. And these values range from 0 to 255. So if you have a white pixel here, then that's just 255, which is the maximum intensity. Or if you have a black pixel, then that would be 0. Okay, and then if you have gray values here with different levels of brightness, then they would range from 0 to 255 as well. So you have things like 127, 145, 175, and so on. Okay. Now, when you create an image with a camera, so these are the ingredients of creating an image. So first, of course, you have the scene, okay, what you're going to capture, the imaging system or the camera, and then the illumination source or light source. Okay, so the camera captures the scene with the help of the illumination source. Okay, and then the camera creates the image as the output. Now, without the energy source or the light source, then our image would be maybe just pure black, because in the absence of light, then you cannot capture anything, right? Or maybe there's something there, but it's too dark, right? That's why lighting is important in creating an image. Okay? But remember also that in the process of creating the image or a digital image, the digitization causes the digital image to become an approximation only of the real scene. Okay? So, although we want to capture the scene, we can only create an approximation of that scene. So, for example, here we have a smooth, pear-shaped object, but in our digital image, it will only be an approximation. Like if you zoom into that, the edges here are not really that smooth. Okay, so it just looks smooth because maybe there's a lot of pixels here, such that the jaggedness, or the not you can't see anymore that it's not smooth. But if you zoom into that, then you can clearly see the boxy feel of the image, right? Because as we know, the image is made up of individual pixels. So the pixels are in square shape. So that's why the edge here is not really totally smooth. Okay, if you zoom into it. Okay, so it's only an approximation. So that's why if you have like a low resolution image, you call it pixelated, right? Because it looks like this, wherein it you can see clearly the pixel delineations or the boxy feel of the image. It's not that smooth. Okay, so because of that, there's a lot of noise and there's a lot of like boxiness feel to the image that we want to remove, and that's why we have image processing. Okay, so image processing is basically just performing an operation on an image. Okay, so you can do analysis on the image, you can do manipulation on the image, and that is what you do when you are processing the image. So image processing is basically just a function that takes an image, does some stuff with it, and then you output an image also, wherein you have done some operations on it. Okay, so input is an image, output is also an image, and in between the process there are some operations that you do to perform or to achieve what you want to achieve, right? So may that be improving the quality of the image or removing noise and so on. So whatever the purpose is, then you do your image processing. Okay, so why do we do image processing? First, I already mentioned this, so you could enhance the image quality by doing processing. You can remove the noise, okay, or you could also use it to extract useful information like segmentation, like automatically detecting some parts. Okay, so those are the some of the reasons or the main reasons why we do image processing. So
quality, improving image quality, removing noise, and extracting information.
So some applications of image processing, you can do this for microscope images in biology. So you can enhance the images that you take from the microscope so that you can clearly see the cells and the I don't know, I think these are germs or microbes or whatever. And in astronomy, you can use image processing for space images so that you can get a better visualization of what is out there in the outer space. You can also use it for medicine, right? In medical imaging like CT scans, X-rays, to improve the quality and so that the doctor can see the structures or the parts better. You can also use image processing to improve biometric images like fingerprints, right? So so that you can match the fingerprint better, okay, or with more accuracy. You can also apply it to satellite images for weather forecast, right? And for like maybe urban planning, check which regions are flooded or something. Satellite imagery to detect the buildings and the structures or the layout of the city automatically. So you can also do that. And of course, you can just simply apply it to your personal photos, right? So just for your personal consumption. So what can we do with image processing? So we mentioned noise removal, right? So for example, if you have a really old image, then there will probably be like salt and pepper noise in there. So just like this. So the little dots that you can see here, those are what we call salt and pepper noise. Okay, so it kind of lowers the quality of the image. So if you want to remove this noise, then you can process the image to remove the salt and pepper noise. Okay, so this one here is the denoised image. So you'll notice the dots aren't that visible anymore. They are still there, but we've at least lessened the number of noise. Okay. You can also do things like improve the quality of the X-ray image. So for example, in here in the original image, it's too dark in this area to be able to see the ribs. So by doing image processing, you can brighten this area here, and the doctor can see the ribs more clearly. You can also use it for things like the processor processor chips, right? So this one has salt and pepper noise also. So if you remove the noise, then it looks better, right? And then for this one, a aerial view of the city. This one has like washed out feel, so it's too bright, right? And you can't really see the structures clearly because it kind of blends together, or it's washed out. So by doing image processing, you can also improve the contrast so that you can see the structures better. Okay, so that's the next one, which is contrast adjustment. Okay, so by contrast, we mean that the foreground or the main object pops out of the background better. Okay, so if it has low contrast, then the foreground and the background kind of just blends together, right? So here we don't want this usually because it has low contrast. So the house here or the remnants of the house kind of blends with the background with a grayish color, right? So if you want high contrast, then we have this one. Okay, so the house here, the structure, just pops out more from the background. Okay, so you can see it clearly. It has high contrast. Okay, so you can also do that. And then we can also do things like edge detection, right? Detect the edges in the scene. So for the building here, there's a lot of edges. So you can also do that. And then of course, region detection, you can use it for segmentation. So especially in like medical images, so you can isolate certain parts of the brain or the whatever it is that you're looking at much clearer and much easier because we can do automatic detection and segmentation. Okay, and you can also use this for image compression. So having the same image but with much less space that's being used in memory, right? So for example, if you have the PNG and then you convert it to JPEG, then there is some image processing that's being used to conserve the information but use fewer data, right? Or fewer bits than the original. Okay, so those are the applications. Oh, one more thing is you can also do this for digital in painting. So if you have damaged image from before, from maybe this is an old photo, so there are creases here wherein it shows where you folded it. So maybe this was kept in the pocket of someone, so it was folded, and through time this creases became much more prominent. So if we want to improve the quality of this image without this lines here, we can do digital in painting, which is basically just estimating which pixels should go in this lines here, okay, so that it becomes a much better image without the lines. Okay, so for image processing, we usually have two types of operations. So point operations and neighborhood operations. So for point operations, those are just operations that work on pixels individually. So it's just 1:1. So you just look at individual pixels, transform the value of that pixel, and then save that as the transformed in the transformed image. Okay. So for example, in the previous video we talked about image arithmetic, right? So you can darken the image by subtracting a value, or lighten the image by adding more value. So if you subtract, like let's say -128, then the pixels become darker because it becomes closer to 0. But if it's +128, you add more brightness, then it's closer to 255, so it becomes lighter. You can also do the invert or the negative effect, so 255 minus the image. You can have lower contrast by dividing it by 2, or higher contrast by multiplying it by 2. Okay, and other transformations that you can do. This is basically done for each pixel individually, and then whatever is the value, that is what is saved on the transformed image. Okay, so it's just a one-to-one correspondence between the pixel in the original image and the pixel in the transformed image. Okay, now on the other hand, there are also operations that work on a neighborhood of pixels. So it's not just 1:1 anymore. So for one pixel here, it will actually look at a neighborhood of pixels. Okay, so maybe the top, to the left, to the right, to the bottom, and then diagonals. Okay, so depending on the size of the neighborhood, it could consult the neighboring pixel values before combining them and settling down for what is the final value of this individual pixel. So it's not just 1:1 anymore. So one pixel will consult the neighborhood before finalizing its value for the transformed image. Okay, so one example of this is convolution, which we will talk about more in the later part of this video. But basically for convolution, you are looking at a neighborhood of pixels like this. So this is your neighborhood, and then you assign some weights. So maybe the one with the most weight here is the one on the right, so this is 0.9, and then the one with the least are the negatives, so -1, -1 here. So you apply those weights and then apply the value of the pixels in the neighborhood before finalizing the value of this individual pixel here. So we'll talk more about convolution later during the filtering part. Okay, but those are the two types of operations. You have point operations, which work on individual pixels, and then neighborhood operations, which work on a neighborhood of pixels to compute the value of one pixel. Okay, so let's now go through different image processing techniques, starting with histogram equalization. But before we discuss histogram equalization, of course, we have to know what a histogram is. Okay, so a histogram is basically just a graph that shows the distribution of pixel intensities. Okay, so in an image you can see the brightness values, because it will show you are there more pixels that are bright, or are there more pixels that are dark, because it's just a graph that shows you this is the number of 0 pixels, this is the number of 125 pixels, or number of 255 pixels, and so on. Okay, and you can also see the contrast basically in the histogram, because if it's concentrated on just one area, then it has low contrast, right? Because it's like, let's say if it's pure black, then all of the pixels, or all the graph will just show everything on the zero marker. But if it has high contrast, so there are dark pixels and bright pixels, then there would be like peaks at different areas, right? So to calculate the histogram of an image, we use cv2.calchist. Okay, so calculate histogram as the function. Okay, and then to plot the histogram, to show the histogram itself, we will use the matplotlib for plotting. So we will plot the histogram using this piece of code, and basically it looks like this. So if you're looking at a grayscale image, then it will just, of course, see the distribution of brightness or intensity values, so from 0 to 255. So in this one, it tells us that there's a lot of like bright pixels, around 200, somewhere here, right? 200 area, and there's only a few like dark pixels, so from 0 to 50, it's not that much. Okay, but in this range here, it's at around 12,000 number. Okay, so it just tells us the distribution of pixel or intensity values in an image. Okay, now you can also do this for colored images. Okay, so for this one, I separated the red, blue, and green channels, and I plotted each channel individually. So for the red one, there's only like a few, like at 100 range, and there are also a few at 255 because of this red bridge here, but that's not the majority of the picture. For the majority of the pixels are at blue, because in here you can see the blue line peaks at around 250, the 250 range. So this is pure blue because of the sky and the water right here. Okay, now green is also kind of abundant in this image, right? So it peaks at around the 200, between 200 to 250 also here, right? Because of the plants here, or the shrubs or the trees, I think. And then there's also green along the mountain, and yeah, so you can check this or use the histogram to check like the levels of redness, the levels of blue, levels of green for the image. Okay, so that is the purpose of the histogram. Now, what is histogram equalization? So for histogram equalization, it's an image processing technique that improves the contrast of an image by stretching the distribution of pixels. So what do you mean by this? So if it's a like a bad contrast image, then this will just be like concentrate the distribution of pixels will be concentrated on one area. Okay, but if it has good contrast, then it would be more distributed. Okay, so we usually apply this to grayscale images. Okay, and we use the cv2.equalizeHist as the function for histogram equalization. So let's see some examples. So if this is the original image, okay, this is its histogram. So you'll see that it's more concentrated on this area here, right? And okay, so let me take out my pen. So the distribution of pixel intensities are distributed in this area, right? But the pixels here are not so much. There aren't many pixels along this range. So for histogram equalization, what it does is it kind of stretches this histogram so that it becomes kind of more or less not really equal, but more distributed. Okay, so that it has more pixels around here, and then instead of having peak here and then without any pixels at the 255 as well, it will give you pixels here at this range as well. Okay, so with that stretching of the histogram, okay, you have better contrast now, because like for example here at this part it became white, so you can clearly segment these parts here, the black from the white, whereas here this was black to gray, so maybe there's less contrast. Okay, so it improves the contrast of the image by stretching the histogram. So let's see more examples. So here, this one is really terrible histogram, because the pixels are concentrated on this part here, right? So let me bring out my pen again. So everything is in this part right here. It's because the image is too dark, right? So it's concentrated on the 0 part of the range, right? So it's too dark, so everything is concentrated here. But when you apply histogram equalization, then you kind of distribute a lot of these pixels into other parts, like right here, which aren't as abundant. So when you stretch that, the image becomes much more brighter and with better contrast, such that we could see the structures more clearly now. So the arcs are here, the arcs are here, whereas in here the details can't be seen right here, right? But in here the details are much more visible because of the better contrast. Okay, and then final example, this one is not that bad, but like it's more or less concentrated here as well. And then when you stretch that, then at least the peak is much less steep. Okay, so it's much more like distributed now. Okay, and so it has better contrast. Like you'll notice in this area, in here it pops better, right? So it's much more visible. And then even in like this area here and in here, it pops better, right? It has better contrast. Okay, so that is the purpose of histogram equalization. Okay, you stretch the histogram so that the pixels aren't distributed in one area, and then it leads to better contrast for the image. Okay, so that's histogram equalization. Okay, next let's see thresholding. So for thresholding, what we do is we change the pixel values based on some threshold value. So we change everything based on a single value, which is the threshold or the boundary. Okay, and we usually apply this to grayscale images. Okay, so one channel only, and we do this to produce binary images. So binarization is the process of turning a grayscale image to a black and white image. So in a binary image, the pixels are either just 0 or 255, either black or white. Okay, so it's not grayscale anymore, it's purely black or white. Okay, so that's a binary image. So we have different thresholding types, and these are the flags that we'll use. So thresh binary inv, thresh trunk, or which is for truncate, thresh to 0, and thresh to 0 inv, which is invert. And these are the explanations for each one. So for the let's say that this is the original image. For binary, once you reach the threshold value, okay, so let's say the threshold is at somewhere at the middle. To the left of the threshold value, it will become black. To the right of the threshold value, it becomes white. Okay, so values, pixel values that are less than the threshold will be black, and pixel values that are greater than the threshold will become white. For binary inv, it's well, basically the invert. Instead of black on the left and white on the right, it would be white on the left and black on the right. Okay, but it's basically the same, it's just we flip the black and white. For truncate, from 0 up to the threshold, it will be the same as the original image. So just like here, right? So it's the same. Okay, let me bring out the pen again. So up to the threshold, which is somewhere here, then it's similar to the original image right here, right? But from the threshold upward, okay, it becomes white. Okay, and then for to 0, that would be from 0 up to the threshold, which is somewhere here, it becomes black. But from the threshold up, it becomes the original image, which is right here. Okay, so that is the same as this one. Okay, and then finally for to 0 in, it's basically the same as to 0, but the opposite. So it's instead of from you go from 0 up to the threshold, it's the original, and then from the threshold upwards, it becomes 0. So it's basically just like trunk, but instead of white here, it becomes black here. Okay, so those are the different thresholding types. Okay, so first let's look at simple thresholding, wherein we use a global threshold value. That means that we just use one threshold for the whole image, so it's a global value. Okay, so like for example, in this image of Batman, if we apply the threshold of 127, then all of the pixel values that are less than 127 would become black. Okay, so the dark pixels become black, and everything that is greater than 127 would become white. So there are gray parts here that becomes white, and then depending on the darkness of the gray, if it's super dark like here, okay, so this one here is like dark gray, right? So that becomes black here, but this part here is also gray but kind of light, so it becomes white right here. Okay, so that is how you do global threshold. So basically just one value that decides whether this should be a black pixel or a white pixel. If you're less than the threshold, it becomes black. If it's more than the threshold, then it becomes white. Okay, so you can do this for things like masking and like simple segmentation. If your image does not have a lot of noise, and there's a high contrast between the background and the foreground, so you can easily pick global threshold value to produce the mask itself. So you can do that like for the coins here, or for the apple here, which is high contrast. So it's kind of simple. So the function for OpenCV is called cv2.threshold, and of course you have to manually set the value, but this requires a lot of experimenting depending on the image, right? So it could be 127, or if you're not satisfied, you could lower the value, or you could set it higher. So it requires a lot of experimenting, trial and error, and so it's kind of tedious to do that, but well, the advantage is it's very simple also. Okay, however, the disadvantage is it's bad for images with different lighting conditions on different areas. Okay, what do you mean by this? So let's say for example, this is your image here, so the image of the Sudoku, but different areas have different lighting conditions. Like for example, this part right here is kind of dark because of the shadow, whereas this part right here is kind of lighter, right? So it has better lighting. So if you apply global threshold there with 127, so you apply the same threshold, so obviously it will have bad results because the different regions of the image have different lighting conditions. Okay, so this one is darker, so obviously you need a much lower threshold here, whereas in here you could do survive with having a high threshold, right? So if you apply 127 here, of course this would be 127 would be too high because this is already too dark here. So you would need something like around 50 here to at least make this better. Okay, so if you apply a global threshold to images like this, then it will have bad results. So this is the result of applying global threshold, which looks terrible, right? So with that, we can instead apply something called adaptive thresholding. Okay, and for adaptive thresholding, we don't apply just one value for the whole image. We actually check local regions and have different thresholds for those regions. Okay, so for adaptive thresholding, we look at the small neighborhood area and we find different threshold values for each area, because as we mentioned, this area might have a different lighting condition from the other areas, right? So we will find the threshold value that best fits this neighborhood. Okay, so this will have better results for images with varying illumination, just like our Sudoku example. Okay, so you'll see here adaptive mean and adaptive Gaussian produced a much better result compared to the global threshold. Okay, so what we do is we kind of apply like a sliding window technique. Okay, so we start at the top and then we move the window, going from left to right and then from top to bottom. Okay, so we look at each neighborhood, decide what the threshold is for that neighborhood, and then apply it, and then go to the next neighborhood, and so on. So it will follow a sliding window approach. Okay, so for adaptive thresholding, we use the function cv2.adaptive_threshold, and we have two methods. We have the mean or the average, or the Gaussian, which is like the bell curve, right? So you need to set the block size or the size of the neighborhood area. So how big of a neighborhood are you looking at? So it could be like, think 3 by 3 or 5 by 5 or 11 by 11. So depending on how you want it to be. But usually we just use 3 by 3 or 5 by 5. 11 by 11 is too big, but in some cases you might need like a bigger neighborhood, depending on your application. Okay, so again, these sizes will dictate how much, or how big is the neighborhood that you're looking at. So how big is this window basically? Okay, so that is adaptive thresholding. So for adaptive mean, we will use the flag adaptive thresh mean C, wherein the threshold is the average of the neighbor values. So if you're using, let's say, a 3 by 3 window, then let's say right here. Okay, so to decide for this pixel at the center, we will check all of the pixel values in the 3 by 3 neighborhood and get its average. Okay, so take the sum divided by 9. That would be the value for the center pixel. Okay, and then for this pixel right here on the next one, okay, let's change the color. For this pixel here on the next one, it will move to this next window here. Okay, so this is another 3 by 3 window, and then it will look at its neighbors, and then it will decide for the value of this next pixel. Okay, and then for the next one, it will move again, it will slide again. So for this one here, it will check another 3 by 3 window here and then decide for this pixel here. Okay, but this would be average of neighbor values. For Gaussian, okay, let me bring it back to red first. For Gaussian, then we use the flag adaptive thresh Gaussian C, and then the threshold is just the weighted sum of neighborhood values. Okay, so the weights are following a Gaussian window, which we will discuss the details of later. But basically, for adaptive mean, for a 3 by 3 window, they all have equal weights, right? So this one would be 1/9. They all have equal weights, right? So 1/9 over everything. For adaptive Gaussian, the windows are much more different. So for example, in this one, the one at the center maybe has more, let's say, more weight. Okay, so maybe this has a weight of 5. Okay, and then at the top, left, right, and bottom will have lesser weight, so like let's say 3, and then on the diagonals maybe just 1 no weight, and then we'll normalize this by dividing it by the total sum, which is 5 times 12 plus 12, that's 17, plus 4, it's 21. So 1 over 21. So this will become weights now. So this will 1 over 21, 3 over 21, 5 over 21, and so on. So this is following a Gaussian curve, because at the center it's much bigger, and then at this one it's like lesser but still higher than the one at the outskirts. So it follows a bell curve like this. Okay, so we'll learn more about this in the later part when we discuss the Gaussian filter itself. But that's the basic difference between adaptive mean and adaptive Gaussian. Okay. Now, next we also have another method for thresholding, which is Otsu's method. So for Otsu's method, it automatically calculates the threshold value for a bimodal image. Now, what is a bimodal image? A bimodal image is basically an image whose histogram has two peaks, okay, or two maximum points. Okay, so to use Otsu's method, we will still use CV2, the threshold, but we will send the thresh Otsu flag. Okay, so this is an example of a bimodal image. So this one is the image itself. Okay, and for its histogram, it has two peaks, right? The one at somewhere here between 50 to 100, and the one right here at 200 to 250. Okay, so what Otsu's method does is, because this is a bimodal image, it will try to find the midpoint between the two. Okay, and the midpoint would kind of become the global threshold value. So it basically means that since I have a lot of pixels right here and a lot of pixels right here, then if I divide it somewhere in between, then that would be a good clean segmentation of the black and the white. Okay, so this is the result of the thresholding for this image using Otsu's method. Okay, so it automatically found 133. So it's kind of similar to the simple thresholding that we did earlier, wherein we used a global value, but earlier we had to manually set the threshold value. For Otsu's method, it will automatically calculate that for you. Okay, so we don't have to experiment whether it should be 127 or 150 or whatever. Otsu's method will automatically find that value for you and set it for the global value. Okay, so yeah, however, we mentioned that it works mostly for bimodal images. So if you don't have a bimodal image, it also does not work as well as intended. Okay, so let's take a look at this example here. So let's say this is the original noisy image, okay, and this is the histogram, right? So it doesn't have two peaks, it kind of only has one. So if you follow the global thresholding of 127, then this would be the result. So you kind of separate the black from the white, but there's also a lot of noise inside because it's a noisy image, right? Now, if you apply Otsu's thresholding on this image, right, wherein its histogram only has one peak, so it doesn't work as well, because you'll notice that it still has a lot of salt and pepper noise, right, on the black, and then even at the white part, it also has salt and pepper noise. Okay, now if we applied the Gaussian filter to this image, to this noisy image, to reduce the noise, then we kind of blur it using the Gaussian filter. So we'll learn more about this in a while, but if we apply this, then the histogram of the image, the filtered image, becomes bimodal. So it now has two peaks, okay, because we kind of removed the noise. And now if we apply Otsu's here, that it has a now that it's a bimodal image, so now that it has two peaks, then the results look much better, because Otsu's method again works best for bimodal images. So it now has a cleaner segmentation of the black versus the white without a lot of the noise. Okay, so that is Otsu's method. Okay, so those are the three techniques for thresholding. So you have the simple threshold, wherein you just use a global value, and then Otsu's method, which calculates the global value for you automatically if you have a bimodal image, and then of course the adaptive threshold, wherein you kind of find a different threshold value for different regions or neighborhood of values. So which works best for images with different lighting conditions and different areas. Okay, so that is thresholding. Next, let us look at morphological transformations. So what are morphological transformations? So these are operations that are based on the shapes in the image. So that's why it's called morphological. So morphology is basically shape, right? So we usually perform this on binary images. So if you don't have a binary image, you perform thresholding first to binarize it. Okay, so it has to be black and white. And the OpenCV function that we'll use for morphological transformations would be the morphology X method. Okay, and you can even repeat the morphological transformations if you want to. So you pass in the iteration parameter, and then you set how many iterations of this particular transformation you want to do. So if you want to erode it 5 times, then it will repeat that 5 times, and then it will erode the image. Okay. For morphological transforms, we will need something called the structuring element or the kernel, and basically it's just a small matrix of pixels which is set to 0 or 1, and the kernel sizes are usually 3 by 3 or 5 by 5 or even 7 by 7, but usually the dimensions are square and odd number. Okay, and we use the method get structuring element to get this kernel. Okay, so examples of kernel shapes would look like this. So this one is a square 5 by 5 element, so it has 5 pixels across, 5 pixels downward. So 5 by 5 na square. Now this one is a diamond shaped 5 by 5 element. So it looks like a diamond because the pixels that you will look at, so those that are activated by 1 looks like a diamond here. So the ones here that are 0 will not be looked at. Okay, and then this one is a cross shaped structuring element, so only the ones across horizontally and then downward, so the diagonals don't matter in the 5 by 5 element. Okay, so you can choose which parts are going to be considered in the morphological transform. Okay, so those are the kernel shapes. So these are the 7 different morphological transforms that we will discuss. So we have erosion, dilation, morphological open, morphological close, morphological gradient, top hat, and black hat. Okay, so let's go through each one. So erosion is basically shrinking the image. Okay, so it has a skinnier version, whereas dilation kind of dilates it or makes it fatter, right? And then for gradient, you kind of get the outline of the image. And then for morph open, you kind of remove the salt and pepper noise here, the dots, the tiny dots. Okay, for morph close, you kind of remove the holes inside. And then for top hat, you get the salt and pepper noise. And then for black hat, you get the holes inside. Okay, so let's go through each one in detail. So again, for erosion, you kind of decrease the thickness of the image, so you erode it. Okay, so basically the rule here is, if the pixel that you're looking at is if all the neighbors of the pixel, okay, is white, then you will also be white. Okay, but only if all neighbors are white. If one of the neighboring pixels are black, then it will automatically be black as well. Okay, now we say here all neighbors, but this is dictated by the structuring element. So the neighbors that it will look at are those that are activated by 1. So in here, if it's a square square kernel, then it will look at everything in the 5 by 5 neighborhood. But if it's a diamond kernel, then it will only look at this pixels here or these neighbors here without considering the ones that are in 0. Okay, so those are what we mean by all neighbors. So all neighbors that are activated by the kernel. So looking at all neighbors, if all of them are white, then you will also be white. But if one of them is black, then you're automatically black. Okay, so the function for this is called cv2.erode. Okay, so it will decrease the thickness of the image, and we'll see why in a while. Now the opposite of this is dilation. So you dilate or you increase the thickness of the image, and the rule for this one is if any of your neighboring pixel is white, then you will also automatically be white as well. Okay, so we don't mean to sound racist here with the black and white talk, but what we're referring to is black and white pixels. Okay, so if any neighbor is white for this pixel, then you're automatically white as well. And then we use the cv2.dilate function. And then for morphological gradient, we use this to get the outline of the object. And to do this, we use the dilation, and then we subtract the erosion. So dilation minus erosion will give you the outline of the object. And we use cv2 morph gradient as the flag for this one. So looking at the three, so erosion, okay, let me bring out the pen. So for erosion, we decrease the thickness because, for example, for the pixels here along this one, they have black neighboring pixels, right? So once we like examine these parts here, they will become black because some of their neighbors are black. So that's why the ones here are became black. So the ones here at these edges, the edge part, became black, and that's why it became thinner. So only these parts here, the pixels inside, wherein everything, all of its neighbors are white. So this part here, all of its neighbors are white, all of its neighbors are white. Those remain white in the eroded image. Okay. Whereas for dilation, it's the opposite, right? For dilation, if any of your neighbor is white, then you also become white. So the black pixels here, somewhere here, became white because if you check the window here, for example, there are white pixels that are being included. And for dilation, if any neighbor is white, it becomes white as well. So that's why it becomes fatter, or it becomes dilated, right? And the only pixels that remain dark or black are those that are totally surrounded by black pixels also. Okay, so if it doesn't have any neighboring white pixels, then it will remain black. And then for gradient, you get the difference of the two. So if you get the fattened version, then you subtract the skinny version, then you get the outline of the two. Okay, so it looks like this. So morphological gradient. So it's kind of the skeleton, right? So those are the first three morphological transforms. Let's look at the rest. So for morph open, it's an erosion followed by a dilation. And what does this achieve? So it removes the tiny dots, the noise. Okay, so we accomplish this by eroding first. So by eroding, we kind of remove the tiny dots, and the original object also became skinny. So we have to follow that up by a dilation to move it back to its original size. Okay, and then we use the flag morph open for this one. For morph close, it's a dilation followed by an erosion, and this is used to close the small holes inside an object. Okay, so we use morph close for this one. So we'll see the details of this in a while. But for top hat, we want to retrieve the tiny dots noise that was removed by morph open. So it's basically the image minus the morph open to retrieve the tiny dots noise. And we use the flag morph top hat. And then for black hat, we retrieve the small holes that we covered up in morph close. So it's the morph close minus the image. Okay, so we use the morph black hat flag for this one. So these are the four things, right? So morph open is erosion and then dilation. Okay, so when you erode, all of this black small white pixels here would be removed because they would be swallowed by the black neighbors here, right? So by erosion, we make this small white pixels here disappear because they are covered or they are surrounded by black pixels, right? So when we erode, all of them will disappear, but we will also make the original J here skinnier. So that's why we follow it up with a dilation, because this time those noise, salt and pepper noise are removed, but when we dilate, we just bring the original image back to its original size, right? So that's morph open. And then for morph close, if there are tiny holes inside your object, then maybe we could do a dilation first. So when we dilate, these holes here are filled in because they are surrounded by white pixels, right? So this will be filled in, but the original image will also become fatter. So we have to follow that up with the erosion to make it go back to its original size. Okay, so we remove the holes and then we bring it back to its original size. Now, for top hat, what if you were interested in this noise instead? We don't want to remove the noise, but we actually want to extract the noise. Okay, so maybe you're doing things like dandruff analysis, maybe. So this tiny flecks here are what you want to retrieve. So what you need to do is just the image minus the morph open. So if you get this image and then you subtract the clean version, then you'll just get the tiny dots noise, right? So maybe if you want to do dandruff analysis, you can do something like that. And for black hat, so if you're interested in the holes instead, right? You want to retrieve the holes. So maybe if you're doing something like analysis of a leaf, right? So maybe there's a leaf and then there's holes in the leaf, like from caterpillars or whatnot. Then you want to analyze the size of the holes and whatever. Then maybe you want to retrieve the holes, right? So what you want to do is you want to get the original image minus the morph closed, and then you'll get the holes instead. Okay, so that is the 7 different morphological transforms. Again, you can only do this for black and white images because it has to be binary, because of the transformations that we're doing depend on whether the pixel is black or white. Okay, so those are morphological transformations. And finally, we will go to the last part of our image processing lecture, which is all about filtering. So you're already familiar with filters, right? Filters are very much abundant nowadays in Instagram filters, Snapchat filters, even in Messenger. There's a lot of filters as well. So basically, a filter is something that you apply to the image to improve the quality or change the overall appearance or something, right? So formally, a filtering is defined as follows. Filtering is modifying the pixels based on some function, okay, of a local neighborhood of each pixel. Okay, so you modify the pixels based on some calculations based on the local neighborhood. Okay, so we're still looking at a neighborhood of each pixel. So why do we do filtering? So the purpose of filtering is to remove noise, to blur the image, or to sharpen the image, or basically to transform the image into another like a different looking image. Okay, we will distinguish between low pass filters versus high pass filters. Okay, and then for low pass filters mostly focus on blurring and removing noise, whereas high pass filters mostly focus on sharpening and detecting edges. Okay, so linear filtering, or also known as convolution, is the process of replacing each pixel by a linear combination or a weighted sum of its neighbors. Okay, so you look at the neighbors, so it could be a 3 by 3 neighborhood, a 5 by 5 neighborhood, and then you do some sort of linear combination wherein some neighbors are assigned weights. Okay, so it could be a uniform weight or it could be a Gaussian distribution, so we'll see the difference in a while. But basically you combine them, the pixel value and the weight of that neighbor, and then when you combine them, that would be the new value of that pixel. Okay, so the kernel or the filter itself will hold the weights that control the linear combination. So we kind of alluded to this earlier when we did mean versus the Gaussian, but yeah, it's basically the same. Okay, so if you have a mean filter, then it would have an equal weight across the different neighbors. But if you have a Gaussian filter, maybe the ones closer to the center would have a higher weight than those that are far away from the center. Okay, but whatever that is, okay, whatever it may be, it would be the filter or the kernel that will hold the weight that will control the linear combination. Okay, so usual kernel sizes are 3 by 3, 5 by 5, 7 by 7, 11 by 11, and so on, but it's usually square and odd numbered. Okay, so that it has a center. Okay, so the basic idea for linear filtering would be like this. So let's say that this is your image data and then this is your kernel. So the kernel would tell you the weights, right? So for this one it would be 0.5, this one would be a full 1, and then here it would be 0.5. So for the convolution or the combination, and then the rest is 0, right? So this values here would be ignored because their weights are set to 0. And then this one would be 0.5, so that would be 6 times 0.5, it's 3, right? 6 times 0.5, and then 1 times 1 here is just 1, and then 8 times 0.5 is 4, so half of 8 is 4. So if you add all of them together, it would be 8, and so the value for this pixel here would be 8. Okay, so that is basically how you do linear filtering. Okay, weighted sum of the neighbors. So the actual math of that is for the convolution is flipped dot product. So it's a dot product, but you kind of flip the kernel. Okay, we won't go into the details of the math equation, but it's basically just a dot product. Okay, and then you apply this again as a sliding window. So for each window, you apply the kernel, you compute the weighted sum of the neighbors, and then that would be the value of this pixel, and then you move to the left, to the right. Okay, you slide this window, and then after you're finished with this row, you go down, and then you slide it again to the right, and then you go down, slide it to the right, and so on. Okay, so this is the sliding window for convolution. So for the steps, you flip the kernel horizontally and vertically because it's a flip dot product, and then you slide the kernel on the image, you multiply the corresponding elements, and then the sum of the products would be the new value for that pixel, and then you repeat until all values are calculated. Okay, so those are the steps for convolution. So for example, if this is your weight, this doesn't really do anything because it just has a 1 for the center image, center pixel, and then 0 for the neighbor, so it doesn't really do anything. So we call this the no filter. So the original, if you apply this filter on this image, it will just be the same image. Okay, because it doesn't really consult the neighbors, right? It has 0 weight for all the neighbors and then just 1 for the same pixel. This one is called shift left because you're looking at the pixel to the right, to the left, and applying 1 or the full weight, and then the rest would be 0. So you're basically shifting everything by 1 pixel to the left. Okay. This one is called the mean filter or the blur, wherein you're doing a blur. So basically everything has a 1 over 9 weight. So equal weight for all the neighbors. So 1 for everything, and then we normalize it by getting the sum of everything. So the sum of everything is 9, right? So we multiply it by 1 over 9. So the weight of everything is 1 over 9. So it has equal weight across all neighbors, and so this will practically blur the image. If you want to sharpen it, you could do things like times 2 of the original and then minus the blurred version. So we'll come back to this later when we do sharpening, but yeah, you can do that. So you can multiply it by 2 and then you subtract the blurred version to make it sharper. Okay, so we'll take a look at low pass filters first. Okay, so for low pass filters, their focus is on removing noise and blurring the images. Okay, so we have the mean filter or the average filter, the Gaussian filter, the median filter, and the bilateral filter. So we'll focus on these 4 filters for the low pass. Okay, so let's start with the mean or average filter. So it's really simple. The new value for the pixel would be the average or the mean of all the pixels under that kernel. Okay, so whether it's a 3x3 neighborhood or a 5x5 kernel, depends on the size of the kernel, and it will take the average of those values. Okay, so we will use cv2.blur or cv2.box filter for OpenCV to use the mean or average filter. And what you need to set is, of course, the kernel size, so whether it would be a 3x3 neighborhood or a 5x5 neighborhood, and so on. So example of the mean filter in action would be something like this. So this is the original image here, and then this one has a 3x3 mean filter. This one has 5x5. This one has 7x7, or actually this one is 11x11. Sorry. And you'll notice that as you make the filter size bigger, then it would also become more blurred. Okay, but basically it's just removing some of the noise or some of the details. Now for the mean kernel, we said that it's equal for all neighbors, right? So 1 for the weight is all 1, and then normalize it by dividing it by 9. Okay, so that is for the mean kernel. For the Gaussian, on the other hand, we already kind of mentioned this earlier, but it follows a Gaussian curve or a bell curve, right? So maybe at the center it has the most weight, which is 41, and then at the immediate neighbors, which is the up, down, left, right, it has 26. So kind of high, but not as high as the center. And then somewhere along here is 16. Okay, and then at the diagonal, the ones here would be kind of 7, and then here would be 4 right here, and then at the outer part is 1. So it kind of follows like a bell curve, like that. So in here is 41, and then here is 26, and then 16, and then 7, and then 4, and then 1. Okay, so the closer you are to the center, the higher the weight. Okay, and then as you go outwards, you kind of lower the weight. And then of course we normalize it by getting the sum of everything. So that's 273. So you divide everything by 273, so that the actual weight here is 1 over 273, 4 over 273, and so on. And this one would be 41 over 273. Okay, so that they become actual weights from 0 to 1, between 0 to 1. Okay, so this is the Gaussian kernel. So for the Gaussian filter, the new value is just the weighted mean of all pixels under the kernel, but we use the Gaussian kernel that we discussed in the previous slide. Okay, so we use this to remove Gaussian noise, and it's a more natural blurring. It produces a more natural blurring compared to the mean filter. Okay, because Gaussian is much more natural. That's why Gaussian filter is a popular blurring filter compared to the mean filter. And we use the we use the method Gaussian blur for this one. And we need to set 2 things, which is the kernel size, so the size of the window, so it 3x3 or 5x5 and so on, And we also need to set the standard deviation, or the sigma. And the standard deviation will just control how wide the curve is. So if you have a small standard deviation, then the curve would be steep. Or if you have a wide standard deviation, then the curve would be wide as well. Okay, so what would be the effect of standard deviation? So the sigma, or the standard deviation, if it's 1 pixel, then you don't really notice the blurring at all. If it's 5 pixels, then it's kind of wider, so you kind of notice the blurring now. And if it's like at the extreme, when it's 30 pixels, so the Gaussian window is really the Gaussian curve is really wide, then you'll notice it's very blurred now. Okay, so the amount of blurring depends on the standard deviation. Okay, so yeah. Now, if we compare the mean and the Gaussian filter and its effect, okay, so let's kind of zoom into this image. So for the mean filter, it uses just a box, right? So a box of the neighbors, right? So equal weight for all the neighbors. Whereas in the Gaussian filter, it also uses a box of neighbors, but because of the Gaussian window, it kind of looks like a circle, right? Or a curve. So you'll notice the difference between the this one has mean filter applied. So you'll notice there are streaks of like a lines, kind of lines here, streaks of boxes. So you kind of see where the boxy feel of the filter is being applied. So you'll notice that there are traces, right? So you can see the trace of where the filter passed through. Whereas here in the Gaussian filtered image, it kind of looks smooth, right? It's smoother. Whereas here there are traces of the box, so it doesn't look quite as good as this one. So it's smoother when you use Gaussian filter. Okay. Now next we have the median filter. So for the median, the new value is the median of all pixels under the kernel. So it's not like the average, but the middle value of the pixels. So remember the difference between mean and median, right? So if you have a mean, for the mean, let's say that the values are 1, 2, 3, 4, and let's say 10. So the median of this, or sorry, the mean would be, so what is the sum of this? 14, 17, 18, 19, 20, right? Is that right? 10, 14, 15, 16, 17, 18, 19. Yeah, 20 over 5, right? Or maybe let's make this 100 to make it extreme. So what would that be? So if it's 100, 104, 5, 6, 7, 8, 9, 10. 110 divided by 5, which is how much? Oh no, it's 22, I think. Yeah, it's 22. So the mean is 22. But if you use median, then it's just the middle one, which is 3, right? So you'll see the big difference between mean and median, because mean is much more sensitive to outliers, like 100 here, whereas median is not really that sensitive to outliers, right? So the median is still a value from the original list of values. Okay, so for the mean and the Gaussian filter, the central element could be a new value that it's not part of the neighborhood values, but for median, it's still one of the values that were considered. So the purpose of the median filter is to remove salt and pepper noise. Okay, so we use median blur for this one. So if we want to compare the effect of median filter and mean filter, it would be like this. Okay, so not much visible difference, but that it's because that's not the purpose of median filter. The purpose of median filter is to remove salt and pepper noise. So like this. So there's a lot of salt and pepper noise, and then if you apply median filter, then the salt and pepper noise are reduced. Okay, so those dots there, they're kind of cleaned up. Okay, that's the purpose of median filter, because if you look at the windows here, like for example in this small window, so it will look at black and then some dots here, but majority of the pixels there are still black, right? So that's why for this one it will still tell you that, hey, majority of the pixels here, or the middle, the median of this neighborhood is still black, so it will still give you black. Okay, so that's the purpose of median filters. And then finally, the last low pass filter is called bilateral filter, and the purpose of this is to remove noise but preserve the sharp edges. Okay, so we'll remove noise, so that means that we'll blur it, but we want to preserve edges, because what happens if we apply the normal blurring is the edges will also become blurred. But what if we want those edges to stay sharp? Then we use bilateral filter. Okay, so we use CV2.bilateral filter in OpenCV. So it's kind of similar to Gaussian, but it becomes slower because we're trying to preserve the sharp edges. So example of the bilateral filter is something like this. So you have the different textures here. If you want to blur that, then we'll remove the textures here, but the edges remain the same. Okay, it remains sharp. Okay, so side by side with the Gaussian. So for the original, if you apply the Gaussian, then everything will become blurred, right? So the details are removed. But if you apply bilateral, then the details, like the texture at the shirt is removed, so it becomes smooth, but the edges are still visible, like the shape of the eyes, the lips, the nose, even the outline, it's still visible, whereas in here it's kind of removed already. Okay, so that is bilateral filter. You smooth it, but you want to preserve the edges to still be sharp. Okay, so those are the low pass filters. So we usually do this for blurring or smoothing of the images, right? So we remove the noise and the details to make it blurred. And usually blurring is one of the most used pre-processing step in other computer vision tasks, so that they can perform better. So for example, for segmentation, for image recognition, we might want to blur it so that we just focus on the overall like shape or overall structure of the image without focusing too much on the details, so that we don't really confuse the computer. We don't overload it with a lot of information, because like for example, if you want to do shape recognition, like is it a circle, is it a star, so we don't really need the details of what is inside the object, but we just want to get the overall outline. So we want to blur it, so we remove the other noise and details, and it makes our task much faster and much more accurate, because we tuned out the noise that we don't want to see. Okay, so that's why blurring is a very important pre-processing step for a lot of computer vision tasks. Okay, so blurring is of course affected by the kernel size, the size of the neighborhood. So it could be 3 by 3. So what happens if you have a bigger kernel size? So what if it's 11 by 11? What if you make it smaller? Okay, so that will affect the blurring process. And of course the filter type that you use. Did you use the mean filter, or the Gaussian filter, or the median, or the bilateral filter? Okay, so that will also affect whatever it is that you're trying to achieve. Okay, so that is blurring. Now the opposite of blurring is sharpening, right? So what if you don't want to make it blurry? What if you want to sharpen it? Now it turns out sharpening actually uses blurring, because if we take a look at what blurring takes away, it removes the details, right? So if this is the original, if you subtract the smooth version, what you'll get is you're actually removing the details of the image. Okay, now what if this details here is added back to the original? So that means that it's more detailed now and it's more sharp. It's kind of sharper. So the edges here look more sharper because we added the details back. So sharpening is actually just the original image plus the details which we got from removing the blurred parts. Okay, so this is the purpose naman of high pass filters. So low pass filters earlier focused on blurring the images. Now for high pass filters, it's focused on making images sharper. Okay, so high pass filters are trying to find edges, and we will take a look at Laplacian, Sobel, and Char. So those are the some of the high pass filters that are available in OpenCV, and they use something called gradients. We won't delve too much on the math behind gradients, but essentially you kind of use calculus for this. So you apply gradient on the x-axis and on the y-axis, and that will produce the filter. Okay, so example of the Laplacian filter would be something like this. Okay, so you can see the image, the edges, right? But you also see the noise, because these are also considered as edges, right? And then for Sobel filter, it kind of looks better, but again, these details here are also considered edges because they are also lines, right? So you might want to do some pre-processing to if you want to just get the outline of the Batman object. Okay, so those are some examples of the high pass filters, and then we'll learn more about this when we talk about edge detection, okay, later on in our course. Okay, so that's it for this video. So to summarize, we learned about image processing. Okay, so you take in an image, you do some things with it, and then you output an image also. So lots of applications, from removing noise, improving the image quality, and extracting useful information. Okay, we talked about histogram equalization, which is basically stretching the histogram to improve the contrast of the image. And then we can also do thresholding, which converts a grayscale image to a black and white or a binary image by doing things like simple thresholding, which is using just a global threshold value, or Otsu's method, which calculates that value for you automatically if you have a bimodal image, and adaptive thresholding, which computes a different threshold for different areas of the image, which is useful when you have an image with different lighting conditions on different areas, right? And then we also looked at morphological transformations, which plays on which transforms the image based on the shape, right? So we did erosion to make the image skinnier, dilation to make it fatter, morphological gradient to get the outline. What else? We did the morphological open to remove salt and pepper noise, morphological close to close the holes inside the objects, and then the top hat and black hat to get the noise instead of the like the salt and pepper noise and the holes instead of like cleaning up, right? And then finally we also talked about filtering, so the low pass filters like the mean filter, the Gaussian, median, bilateral filters, which all focuses on blurring or removing details. And then we also talked a little bit about high pass filters, which focuses on sharpening and looking for edges, like the Sobel and the Laplacian filter. Okay, so those are the image processing techniques that you will use as well, a pre-processing step to a lot of OpenCV tasks. Okay, so this will be very useful in other tasks later on. Okay, so in for our next topics, we would talk about image classification next. Okay, so we'll learn more about image classification. So we'll talk about machine learning, some algorithms for machine learning, how important are data sets and the different types of data sets, and what to do with evaluation so that we know whether our image classifier is doing well or not. Okay, so that would be our next topic. And that's it for this video. If you have any questions, please don't hesitate to ask me, and I will see you next time.